Tonight we have an exponential equation with two unknowns, two positive integer unknowns, a single equation. And right off the bat, we see that both 2 and 3 must be divisors of this 5-digit constant, 52488. Okay, now 2 is obvious, right? 2 obviously divides 52488 since the last digit is even. Also, this is the difference of two multiples of 3. Okay, so this is necessarily some multiple of 3. I'll write that 3m. Now also, sum of the digits, people, you can sum the digits here. 5 plus 2 plus 4 plus 8 plus 8 is 27. And if it's a number is divisible by 3 if the sum of its digits is divisible by 3. But it's easier. You can just tell this is a multiple of 3 because it's the difference of two special multiples of 3. Okay, so we know that right now. We know that 2 and 3 are factors of this number. Okay, also just by the form here, m has to be a larger integer, positive integer. Remember, we are talking about positive integers here since the difference is positive here. So we can factor out the smaller exponent n and get this expression. Now, it's nice to have this in factored form because if we can get the prime factorization of our constant, we'll be able to kind of mix and match or equate factor pairs in a manner of speaking. Okay, so let's go on down. Now, we've already seen earlier that 2 and 3 are trivial divisors of the constant. So we know that 2 to the a, 3 to the b must appear in the prime factorization where a and b are also natural numbers. Now, it's clear that 5 doesn't divide this. So 5 does not. We'll put a big slash. We'll negate that relation. 52, 488. Because the last digit would have to end in either 0 or 5 for the number to be a multiple of 5. Okay. Now 7's a little trickier. There's a pretty there's an interesting test on that goes like this: 52, 488. And y'all, the test is this. It's kind of a fun modular arithmetic proof. What you do is you subtract from the number, double the last digit. Okay. So 2 times 8 is 16. And that means this is equal to what? You have to subtract the 16 from the 5248, and so that would give you 52. 16 from that's 32. 5232. Okay, and I won't bore you with the details, but this is not a multiple of 7. Okay, not a multiple of 7. Okay, so that's another test. If what was left, if 5232 was divisible by 7, then the entire number would be divisible by 7. And again, what did I do? You take the last digit, which is 16, and subtract it from 5248. If I did everything right, that's 16 from 5248 is 5232, but that's not a multiple of 7. Now, also the alternating series test, you can do this. You can go 5 minus 2 plus 4. You see how you're alternating here, and there's a reason for that. Plus 4 minus 8 plus 8. I'll tell you why that's true in a minute, but what do we get there? That isn't that equal to 7? Let's see, these cancel, so we get 7, which is not a multiple of 11. If it's a multiple of 11, then the whole thing would be divisible by 11. So I'll put 11m here. Okay? So that's why we know that it's 5 to the 0, 7 to the 0, and 11 to the 0. Now, I don't know, 13 is just a straight up test, but you're going to have to do it. We have to do a big computation at some point, folks. And if you successively divide by 2, you'll find out that that happens 3 times. And so what we actually get here is 5288 is equal to 2 cubed. And now the big computation is coming up with 3 to the 8th. And I won't go through the tree, the tree building, the prime factor tree building. But this is what happens, and this is again, I'll leave out the steps. It's just a tedious computation, but that's what this is equal to. 52,488 is equal to 2 cubed times 3 to the 8th. All right, but watch what that does for us. You see, that's pretty nice, because when we equate, let me just recopy our result up here. Our factored result with this, everything pops out rather nicely. 3 to the m minus n minus 1. Okay, now we know that this 5-digit number is equal to 2 to the 8th. 2 cubed times 3 to the 8th. And again, y'all, I got to stop somewhere. It's just a long process to show that 3 divides at 8 times. But it's not as hard as you might think if you just successively divide. The numbers are getting smaller and smaller. So you see, just by the uniqueness of the prime factorization, okay, we know that 3 to the n, this would imply that n is equal to 8. Right? Okay, n is equal to 8. We have 3 raised to the 8th over here, a prime number. We have a prime number on this side. This is not going to be a multiple of 3 over here, right? So you know that n has to equal to 8. All right. And so we also know that, now that we know that n is equal to 8, that implies from here that we would get 3 to the m minus 8, 3 to the m minus 8 minus 1 has to equal to the remaining factor, which is 2 cubed, which is equal to 8, right? But you can see very quickly that implies that m is equal to 10. Okay, again, by inspection, if you put 10 right here, let me erase that, make it a little bit neater for you. This implies that m is equal to 10. A neater looking 10 there, folks, because you need this to be 3 squared minus 1, right? Certainly equals 8. So those are the solutions, folks. N equals 8, m equals 10. And again, I think it was, it depends on what you mean by hard. It's tedious to go through this prime decomposition and figure out how many prime factors that you have. But, and I didn't conclusively prove that 13 and higher valued primes weren't factors, but I just kept dividing right here, okay? And again, that took some time, and that was the so-called big computation. But so that's the solution, folks. We get m equals to 10 and n equals 8. Good night.